This is the second video preparing you for the March 27th class meeting on exponential models. In this video, I'll work through two more examples using the exponential model, and I'll share some information about how this is related to issues of sustainability. This example highlights how the exponential model can be used for biological functions. Many chemicals in the body are removed at a rate proportional to the amount present. With the case of caffeine, the more caffeine present in the bloodstream, the more that the kidneys can filter out. As the amount of caffeine drops, the kidneys are able to filter out less with each pass. Here, the stock is the caffeine level, and there is an outflow created by the kidney filtering. This gives us a feedback loop that can be represented by an exponential model. Let's work to create an equation modeling this scenario. If we start measuring the caffeine in the body just after you've finished a cup of coffee, we get that S0 is equal to 95. The rate constant is R equals minus 7.17. Note that I'm using a negative here because caffeine is being removed. The time step is 1 hour. Then our equation becomes S is equal to 95 times 1 minus 0.17 to the n, where n is the number of hours since the coffee was drunk. Let's suppose you have a cup of coffee at 8 a.m. How much caffeine will be in your system at 10 p.m.? We calculate S is equal to 95 times 1 minus 0.17, all raised to the 14, representing the 14 hours difference. This comes out to 7 milligrams. Exponentials can also sometimes be used to describe human population growth. Let's apply this to the U.S. population. Here, I encourage you to pause the video briefly and think about how you would try to answer the questions given. First, note that with the information given, we can naturally choose a time step of 1 year and an initial stock level of 321 million people. The rate constant is the percentage change over one time step. Here, we can combine the inflow from births and the outflow from deaths to get an overall yearly change of 1.5 million people. As a percentage of the total population, computing 1.5 million over 321 million, we get 0.0047, or 0.47%. From this information, we can create an exponential model. S is equal to 321 times 1 plus 0.0047, all to the n, million people. And this gives us the estimated population n years after 2015. In 2020, this would be 5 years after our initial population. So we would compute S is equal to 321 times 1 plus 0.0047 raised to the 5th power, giving us 330 million people in 2020. The current U.S. population is actually 328 million people. Note that this model doesn't account for immigration, which is a significant factor in the U.S. population. Our model of the U.S. population also assumes that the birth and death rates are constant over time. Here's a graph of the U.S. population growth over time, which we can see does vary, although within a range of only about 1.5% or so. Notice that the drop in the 1930s corresponds to the Great Depression. There's also a sharp rise in the 1950s. This is the baby boomer generation. Exponential growth in human populations plays a significant role in many systems and has important implications for a variety of sustainability questions. In the first chart shown here, notice that the global population has experienced roughly exponential growth over the past 250 years. This has also led to exponential growth in many other human activities and has corresponding effects on a variety of Earth systems. The growth in the human population and capital has also been intertwined with significant growth in innovations, which is one of the places we look to for sustainability solutions going forward.